If we extend the cotangent graph, we're going to have that same initial curve from 0 to pi. So let's just draw that. And I know that this is at 1 because halfway between 0 and pi over 2 is pi over 4, and we have the point pi over 4 comma 1. This is 3 pi over 4, and 3 pi over 4 corresponded to negative 1. And then we had asymptotes at 0 and pi. So I'm going to approximate the rest of the points so that the curve of cotangent follows more or less what we had on the previous page. Okay, so we're going to have this followed by the same 3 points repeating, but now we have, well, this is 1 pi over 4, this is 2, 3, 4, 5, so 5 pi over 4, 6, 7, 8, 9, this is 10, 11, and 12 pi over 4. Okay, so I'm going to have at 3 pi over 2, you can double check. It's going to correspond to 0. At 5 pi over 4, we're going to get a 1. And at 7 pi over, oh, and this should have been a 4. 7 pi over 4, we're going to get negative 1. Again, I'm just throwing those points at you, but you can always verify by looking at unit circle or by plugging into your calculator. So I'm going to get this curve, and it's just going to repeat. So I've gone ahead and repeated that process in the negative direction, meaning I verified where I have zeros, which happen at multiples of pi over 2, odd multiples of pi over 2, I should say. And I also verified that at negative 3 pi over 4, I get 1, and at negative pi over 4, I get negative 1, that I have asymptote at negative pi, to confirm that this is indeed the curve of cotangent. Okay, so I encourage you to do the same. Make sure that these points agree for cotangent, and then draw the remaining cycles on this graph. We're going to be using them to help us determine the domain. The domain is basically anything that that can be plugged from the x-axis without having any issues. So that'll be from negative infinity to positive infinity, except the places where we have asymptotes, because that is where we'll get something that is undefined. So where do those happen? Well, now they're happening at 0, pi, 2 pi, 3 pi, negative pi, negative 2 pi, basically any multiple of pi. So they happen at n pi, where n is any integer 0, plus or minus 1, plus or minus 2, so on and so forth. What about the range? What y values can we attain? Well, just like in the tangent graph, we can attain any positive y value that we want and any negative y value that we want. There is no break in the continuation of the graph if we're considering going up and down. Okay, so the range will be from negative infinity to positive infinity. For the amplitude, we're going to write NA, because very similar to what we saw with tangent, we have no maximum y value and no minimum y value. That graph extends in both directions forever. And then the period is the place or how long it takes along the x-axis in order for one cycle to repeat, or in order for the graph to repeat. So I can see that one cycle is happening between 0 and pi, and then after that I notice a repetition of the graph. So that means that the period is going to be pi just like what we saw for tan. Okay, so the period is going to be pi. I'm writing p for the period. Okay, what about zeros? Where does the graph touch the x-axis? Well, that happens at negative 5 pi over 2, negative 3 pi over 2, negative pi over 2, pi over 2, so on and so forth. So the pattern that they all have in common is that they are odd multiples of pi over 2. So the zeros are at odd multiples, so that's 2n plus 1 of pi over 2, so times pi over 2, where n is going to be 0, plus or minus 1, plus or minus 2, so on and so forth. Okay, and finally the asymptotes. The asymptotes are going to be given by whatever we excluded from the domain, which in this case was x is equal to n pi, where n is any integer. That brings us to the final definition that is part of this set of lecture notes, and that is a definition for even and odd. Okay, we're going to say that a function f of x is called odd if f of negative x gives you the same thing as negative 1 times f of x. And it's going to be called even if f of negative x gives you the same thing as just f of x. And for both of these, I want to provide you an example. So for instance, if you take a look at f of x equals, and this is an example, so I'll write e.g. f of x equals x cubed, for instance. Okay. If we take a look at what is f of negative 2, well, f of negative 2 will be a negative 2 cubed, which is negative 8. If I take a look at what is f of 2, I'll get 2 cubed, which is 8. So if I take f of 2 and I multiply it by a negative 1, that's going to give me a negative 8, right? So if you notice, both of these are the same answer. That means that f of negative 2 is the same thing as negative f of 2. For something that is even, and an example could be like f of x is equal to x squared. In fact, let me make this a little more complicated. Let's make it x squared plus 3. If you check f of, let's say, negative 2 as well, I'm going to get negative 2 squared plus 3, which is going to be a 4 plus 3, which is 7. And if you check f of 2, that's going to be a 2 squared plus 3, which is a 4 plus 3, which is also 7. Okay, so they both give the same answer. That means that f of negative 2 is equal to f of 2. And it's not just a coincidence. If you try it for any other x value, checking f of any negative value will give you the same thing as f of the positive value. And in the case of x cubed, if you check f of any negative value, that'll be the same thing as negative 1 times f of the positive value. Now, graphically, something very special happens. Graphically, what that means, if I were to graph x cubed, and I'll do it here, it won't be perfect, just so that we can get a rough idea of the behavior. If we plug in a 0, we'll get 0. So there's a point at 0, 0. If we plug in a 1, then we're going to get a 1 cubed, which is 1. If I plug in a 2, so this is 1 and 2. If I plug in a 2, we already saw that that gives us 8. So I don't know if it's going to fit, but we're going to try our best. 2, 3, 4. Okay, let's just make that go in intervals of 2 so that it fits. So this will be a 4, a 2. That just means I'm going to move this point a little lower so that it's a 1, 1. Okay. Then I get a 2, comma 8. So I get something that looks like that. Okay. If you plug in a 3, you're going to get 27, so it's going to continue to curve upwards. If I go into the negative direction, so this is negative 1, this is negative 2, I'll have a negative 1, comma negative 1, so that'll be about here, okay, because this is now negative 2, and then negative 4, negative 6, negative 8. And then at negative 2, well, we'll reach negative 8. So we'll have this curve. So essentially what we're seeing is that this part of the graph that's positive, if you were to rotate it around the x, so using the origin as kind of like a pinwheel, the center of a pinwheel, and you would rotate that pinwheel, you would get that this bottom half of the graph is the same as this part of the graph, but obviously again rotated. And that's going to be true about any function that is odd. If you take that part that is up in the positive direction, it's going to rotate down into across the opposite quadrant, and it's going to rotate in that direction. For the even functions, the graphs will also have a special property. If I graph y equals x squared, I'll get 1, which corresponds to 1. So I'll have that point. And then 2 is going to correspond to 4, right? 2 squared is 4. If I plug in a negative 1, I'm also going to get 1. And if I plug in a negative 2, I'm going to get a 4 as well. And then if I plug in a 0, I'll get 0. So it's a parabola. But what's special about this type of graph is that the points reflect across the y-axis. So what I mean by that is that everything on the right-hand side of the y-axis has a mirror image on the left-hand side of the y-axis, right? These points reflect each other. And the same will be true, it's true about x squared, but it's the same as going to be true about any even function, because by definition, if you take the negative value and plug it into f, you'll get the same thing as the positive value. Okay, so these special properties are called, for even, it's called reflection about symmetry about y-axis. And in this case, we say there's symmetry about the origin. Now we want to see whether the functions that we have talked about so far have any type of symmetry, whether it be odd, even, odd or even. So let's bring back one of our graphs. Here is the graph for sine, and the easiest symmetry to check for is symmetry about the y-axis. If we use the y-axis as a mirror, does the right-hand side of the graph reflect across to the left-hand side? Well, the answer here is no, right? We don't see that type of symmetry. Okay, so it's not going to be even. The next type of symmetry that we should check for is rotation about the origin or symmetry about the origin. So if I take, let's say, just like this part of the graph, which is going up in the positive direction, and I rotate it about the origin, am I going to get the same curve? Well, the answer here is yes. If you take a look, focus just on this little piece of the graph. If you rotate it in this direction, it's going to come and lie directly above this portion of the sine graph. So it's actually an odd function. In fact, if you take this whole portion of the graph and you rotate it about the origin, you're going to get, well, this part of the graph. So sine is actually an odd function. So here we're going to select odd just to test some points and verify that that is indeed the case, because we did it by looking at the graph, but we could also just take some points and verify. If I take, for instance, f of pi over 2, meaning if I plug pi over 2 into sine, well, sine of pi over 2 is going to give me a 1, right? So this is 1. Now if I check what is f of negative pi over 2, meaning if I plug in negative pi over 2 into sine, here's negative pi over 2. For sine, we get a negative 1. So I get negative 1. What we need to check then, is it true that if I take negative of f of pi over 2, that is equal to f of negative pi over 2? Are those two going to be equal? Well, here we're going to get a negative times 1, a negative 1 times 1, and that is equal to negative 1 for f of negative pi over 2. That's a check. So yeah, this even though we've only tested with 1 point, and that doesn't necessarily prove that it's odd in all cases, it does give us a good hint that it might be odd. And then we go and verify by looking again at the symmetry of the graph. Okay, what about for cosine? Well, for cosine, if we look at the graph, for cosine, we said the easiest symmetry to check for is symmetry about the y-axis. If we use the y-axis as a mirror, is it true that the right-hand side of the graph reflects across into the left-hand side? And well, the answer here is yes. If you take a look at this part of the curve, it's reflecting directly into this part of the curve. And then the part that's between pi over 2 and pi, we see it reflect here between negative pi over 2 and negative pi. So again, from the graph, we can judge that it is going to be even, but we can just take a look at some points. If I try, for instance, let's say f of pi gives me, or cosine of pi gives me negative 1. And then if I plug in f of negative pi, well, here's negative pi. It also gives us negative 1. Okay. So in this case, f of pi indeed equals f of negative pi. So we can just, again, it doesn't prove it, but it confirms to us that that cosine is an even function. And we're going to consider one last graph, which is tangent. Okay, here's the graph. And if we focus on reflection about the y-axis, we use the y-axis as a mirror. this part on the right-hand side does not reflect over on the left-hand side. Otherwise, it would look like a parabola. But if I take this top portion of the graph and reflect it about the origin, I would see that it would lie directly above this portion of the graph. So we have the suspicion, or from the graph, we can pretty much see that it's going to be odd. But again, we can just test some points. Let's try f of pi over 4. Tangent of pi over 4. Tangent of pi over 4 is 1. And now if I try f of negative pi over 4, well, tangent of negative pi over 4 is negative 1. So if I take negative 1 times f of pi over 4, I'm going to get a negative 1, right? Because we'll have a negative 1 times 1, which is negative 1. And that is indeed equal to f of pi over 4. Okay. So that means, or that confirms to us that tangent is odd. So these ideas of even or odd are going to be very important for the remainder of the topics that we address in our trig class. So please make sure that you remember these facts and that you also know how to verify their symmetries. What we're going to be taking a look at is what exactly happens when you place a number in front of the sine function, meaning what happens to the graph of it. And I know it's very faint here on the, unfortunately, on the DocCamp, but hopefully it looks a little bit more solid on your live, on your printed notes. But you can see what the graph of sine actually looks like if we don't have any number attached to it. So this curve here, okay, this is y equals sine of x. What we want to do now is figure out what's going to happen when we get 2 and multiply it with sine of x. What's going to happen to the graph? So the way that we're going to do it is we're simply going to take these numbers and plug them into the function just like what we did with the basic graphs. And we're going to get that f of 0 is 2 times sine of 0, which means that we'll have 2 times, if we look at the original graph at 0, sine is 0. So we're going to get 2 times 0, which is 0. That means that we're still passing through the point 0, 0. Okay, that's still part of this new graph. Then for pi over 2, f of pi over 2 is equal to 2 times sine of pi over 2. And again, we can use this one as a reference. Pi over 2 gets sent to 1 for sine, so sine of pi over 2 is 1. This means that we have a 2 times 1, which is going to give us a 2. So the point that we're plotting is pi over 2 comma 2. So at pi over 2, we have a point up here at 2. And repeat the process with pi. 2 times sine of pi is going to give us 2 times sine of pi here is 0, so it's 2 times 0. That means that we have the point pi comma 0, which is this point. Then at 3 pi over 2, we're going to have 2 times sine of 3 pi over 2. And sine of 3 pi over 2, so here it is. And then sine of that is negative 1, right? So we'll have a 2 times negative 1, which will give us a negative 2. That means we'll plot the point 3 pi over 2 comma negative 2. So at this point, we go down to negative 2. Stop there. And then finally, 2 pi. We have f of 2 pi equals 2 times sine of 2 pi, which is going to be 2 times 0, and that's 0. So we have the point 2 pi comma 0. So it's this one here. And so what we see then, if we were to graph that, is that we still have the same sine curve, but it's going to extend lower than usual, and it's going to go up higher than usual. Okay. Do you guys remember what half the distance between the highest and the lowest point was called?
Is it called the period?
Close. So the period actually defines how long it takes to complete one cycle, but it's similar to the period.
Is it the amplitude?
The amplitude, yeah, very good, the amplitude. So what we see here is that we went from an amplitude that would normally be 1 into an amplitude of 2, right? Because now the full distance between them is from 2 to -2. That's a distance of 4, and half of that would be 2. Okay. Yeah, so this here, this amplitude is 2. So that's the main change that we see when we put that 2 on there. You guys have any questions for this problem? This one, we don't need it there. It's just on there as a reference, and so that we can see how the graph is changing. But when you're graphing the 2 sin x, you don't have to have the sin x. Okay. Now, page number 6, we don't really have to do anything for it. This is showing you that the same thing happens to cosine. So if we have the graph f of x is equal to 2 cosine x instead of just the f of x equals cosine x, which is again drawn here very faintly, then you go through that same process of plugging in the x values and then getting out the output y value. And so we get the points 0, 2, which is up here, and then pi over 2, 0, which is here, then pi, -2, which is down here, 3 pi over 2, 0, and 2 pi, 2. So we get this graph. Of course, you can always use more x values to show that the shape of this truly looks curvy instead of straight lines. But just to make it simple for ourselves, we use these points and we trust that the cosine graph will always be curvy. But in comparison to the original cosine graph, we see that the amplitude again has changed. Normally the amplitude is 1, but now it has increased to a 2. And so in this case, we also have the amplitude being 2. And so at this point, maybe we have a suspicion that this number that gets placed in front of the cosine is going to affect the amplitude, and that would be correct, right? Because let's say that this were a 10 instead of a 2, right? Then in the calculation, the 2 would be the only one that changes to a 10. The cosine of 0 would remain the same, and it would still return a 1. So we would have a 10 times 1, which is 10. So that means that the highest point that we would reach instead of being a 1 would be a 10. And then the same thing would go for this. If we have 10 times cosine of pi over 2, we're still going to have 10 times 0. So that would still be 0. So it would still pass through this point, pi over 2, 0. Yes, so the number in front of the cosine or the sine controls how high up we're going to reach and how low we're going to go as well. Let's take a look at another example. On page 7, we have f of x is equal to 1/2 sine x. So the number is no longer greater than 1. Now we're looking at a fraction. And the work has already been done for us. So we just take the x value and plug it in. 1/2 times sine of 0 would be 1/2 times 0. And because remember, sine of 0 is here. It's just 0. So we get 1/2 times 0, which is 0. So that's the point 0, 0. Then for pi over 2, we get 1/2 times sine of pi over 2. And sine of pi over 2 is 1. So we get 1/2 times 1, which is 1/2. That means that we want to plot the point pi over 2, 1/2. Okay, so let's plot 1/2, pi over 2, 1/2 would be approximately there. Then we have pi. 1/2 times sine of pi is 1/2 times 0, because at pi, the original sine graph is 0. So 1/2 times 0 is 0. That means that we get the point pi comma 0. And then for 3 pi over 2, repeat the process, plug it in. Sine of 3 pi over 2 is a -1, and then 1/2 times -1 would give us the -1/2. So here we go down to -1/2, which is approximately there. Okay, and last one, 2 pi. 1/2 times sine of 2 pi means we have 1/2 times 0, which is 0. So that means this point here. So what is that going to look like? Well, we're going to have still a curvy sine graph, but again, the amplitude was affected by this coefficient because we no longer make it all the way up to 1, right? That 1 got multiplied with the half, and that means that the largest value we reach is 0.5, or 1/2. Same thing for the lowest value, right? Normally it reaches the -1, but because it's being multiplied by a half, we end up with a -1/2 as being our lowest value. So that means that the amplitude here shrunk. Normally it's 1, but now we just have 1/2. So any questions so far? And here is a fully worked example again of what happens if it's cosine. So we still have that same coefficient that we had in the previous page, but now we have the cosine graph. So again, plug in the values. 1/2 times cosine of 0 means 1/2 times 1, because cosine of 0 is normally 1. So then we take 1/2 times 1, which is a half. And that means that we have the point 0, 1/2, which is here. For pi over 2, we get 1/2 times cosine pi over 2, which is 1/2 times 0, because at pi over 2, cosine is 0. So then we get the point pi over 2, 0, which is this point. Right, and just looking at the table, we've got pi with -1/2, so that's this point here. Then 3 pi over 2, 0, that's this point, and 2 pi, 1/2, so that's this point. And so it produces, again, this curve that still looks like cosine, but it's not reaching all the way up to 1. It's only making it up to +1/2, and then the lowest it goes is to -1/2. Okay, so we've got this situation of the amplitude still being 1/2. All right. So let me ask you guys this. Now that we know, we've seen examples so far of a number that's greater than 1, a number that is less than 1, but still positive. What do you guys think is going to happen when we multiply by a negative number?
Would it happen somewhat of an inverse, like it goes the opposite direction?
Yeah, very good. So it's actually going to make this graph kind of start down here and then go up in the case of cosine. If it were cosine being multiplied by a negative, very good. And we're going to see why. In this case, we're working with sine, so let's just plug in the values. We've got f of 0 is equal to -2 times sine of 0. So that's a -2 times 0, because remember, sine of 0 begins at the origin, so sine of 0 is 0. We get the point 0, 0, which is here. And then f of 0 is f of pi over 2 is -2 times sine of pi over 2. What is sine of pi over 2 normally? Just evaluating that part. What is sine of pi over 2?
90?
It's 90 degrees, yeah. And what do we get? So here is wait, not this one. Let's see. So here's a sine. I'm gonna put this one up. This faint curve on page number 5 is sine. What happens at pi over 2? It reaches,
The amplitude that it reaches, or 1?
yeah, it reaches 1. Good, yeah, it reaches its highest point, which is 1. So just the sine of pi over 2 by itself would be 1. But then we have this -2 attached to it, which means multiplication, right? So we have a -2 times 1. And that means -2. That means the point we're trying to graph is a pi over 2 comma -2. So it goes down this way. So already we're starting to see this this curve go opposite to the direction it normally goes to, right? Because this is from page 5. This is the f of x is equal to 2 sine x on page 5. And it starts at 0, 0, but it begins curving up into the positive y direction. In this case, we see that it starts at the origin, but it then curves down to the negative y direction instead of going up. And it has to do with that -2. Okay, what about for pi? What is sine of pi? Just that part. What's sine of pi?
Will that be negative? Negative something.
Hey, I got a question, the last question,
Yeah.
Professor. So like, for the sine of pi over 2, it's 1, is it because on the unit circle, it's on the sine side? That's why it's 1 right there?
Yeah, very good. So that's another way that you can also find what sine of pi over 2 is. You can take a look at the unit circle and you'll see that at pi over 2, the point there has a y coordinate of 1. And the y coordinate represents the sine, right? So,
Oh, how'd you do it then, if I found it that way?
so essentially I went back to the original sine, this curve here, which is y is equal to sine x.
Yeah.
And then I looked at pi and then see I looked at pi over 2 and then I saw what y corresponds to this pi over 2. And I see that that is the 1.
Gotcha.
Mm-hmm. But if
Right.
you remember, sorry.
Will sine of pi be 0 or?
Yeah, very good. Sine of pi is going to be 0 because if we take a look at what's the y, where is the graph when we hit pi? Oh, it's at 0. Yeah, very good. And so here we get -2 times 0.
Thank
and then
you.
Christian, just to answer your question, the calculator should be in radians. If you're punching it into your calculator, you would need to be radians. Yes, I'm glad that you guys are thinking about the way that this all ties in, right? So there are basically 3 ways that we can find what these signs are. Okay, the first one is, the first one that I used was looking at the original sine graph, which is either on page 5. We also had it on page, the very first time that we saw it. I want to say it was the first page. Let me see. Yeah. So if you take a look at the very first page of lecture notes, week 8 and 9, at pi over 2, we reached 1. So you can either take a look here or take a look here. It was transferred over from this first page and see that at pi over 2, sine is 1. Okay, so then we write that here. Sine of what was it that we were looking at? Sine of pi over 2, this one. Sine of pi over 2 is 1. The second way that you can look at it is you can go to the unit circle and say, okay, here's pi over 2. I know that the y coordinate represents sine, so sine of pi over 2 is 1. Right. And then the other way that you could do it is if you have your calculator handy, just make sure that you're working in radian mode, because all of these are in radians. And then type in what is sine of pi. So sine of pi is going to be, oh, sorry, we were doing pi over 2, huh? The sine of pi over 2 gives us 1. So 3 different ways you can find this value. And then you bring down the negative 2. Negative 2 times 1 will give us negative 2. So then we know that for this whole thing of negative 2 times sine of pi, when you plug in the pi over 2, you get out a negative 2. Okay, so that's the point that we want to plot.
Hey, Professor, how are we supposed to know when we're supposed to be in degree mode and radian mode? Like, it feels like we switch between them. What is like a way you're supposed to know which one you're supposed to do?
Good question. So anytime that you don't see the degree symbol, that means radians. So all of these don't have a degree symbol, so that automatically means that we should be working in radians.
Gotcha. So no degree symbol, radians, basically.
Exactly. Yeah. The other thing too is, and it doesn't always happen, so this one it gets a little tricky, but if you see pi as part of the angle, that usually means it's going to be in radians. But again, what is for sure going to be true is that you won't see the degree symbol.
Thank you.
Okay, so here we have pi comma 0, which would be this point here. And then for 3 pi over 2, we're going to get negative 2 times sine of 3 pi over 2. And what is the sine of 3 pi over 2?
Negative 1.
Negative 1, very good. So we get negative 2 times negative 1, which is going to be a 2. And that means that we have the point 3 pi over 2 comma 2. Okay, so here's 3 pi over 2. Here's 2. That means that we want to have the point there. And then for 2 pi, repeat the process. We get negative 2 times sine of 2 pi. And that's going to be a negative 2 times, what's sine of 2 pi?
0.
0, very good. So we get the point 2 pi comma 0. So this one here. Okay. All right, and so now we get to draw the curve. We can just estimate, but just always remember these are not straight lines. There's actually a curve to them. It looks like that. All right, so 2 things are happening to this graph when we compare it to the original sine graph. Okay. Here's the original sine graph from page number 1. In the original sine graph, first of all, the amplitude was a 1, right? In this case, what's the amplitude for the one we just did?
Negative 2.
So, well,
Oh,
very,
2.
yeah, so it would be positive 2, and here's why. Remember, the amplitude describes the distance. And so when we're talking about distance, we always think about distance as being something that's positive, right? We can't go a negative distance, like say we can't drive negative 2 miles or that sort of thing. So we always think of distance as being positive. So this has an amplitude of 2. Right. So that's the first thing that's happening. What else is happening to the graph that's different from this original one?
Is it an inverse or?
Yeah, so it's not exactly an inverse in the sense that we've learned it like with this cosine inverse or the sine inverse, but it is like inverted, right? Like it is kind of like reflected over. Instead of starting up in the positives, it goes down into the negatives first, and then goes up and down. Right. So this one we see the way that the textbook describes it, and most other textbooks also describe it, is that there is a reflection about the x-axis. And so two things happen because of that -2. The amplitude changes, and then it reflects about the x-axis. All right. You guys have questions with this problem? Take a look at page 10. Again, this one is completely done for us, so we can just talk about what's happening. But in this case, they're graphing -1/2 times sine of x, and we're still plugging the same x value, 0, pi over 2 pi, 3 pi over 2, and 2 pi. So we get -1/2 times sine of 0, which is -1/2 times 0, so that's 0. At pi over 2, remember, that's when the sine graph reaches its highest point. That's when usually it reaches a 1. But in this case, because we have the -1/2 attached to it, we end up having -1/2 times the 1. So that ends up being -1/2. So that's this point here. At pi over 2, we go down to -1/2. Then when we plug in the pi, we get -1/2 times sine of pi. So that's -1/2 times 0, which is 0. So we still get the point pi comma 0, which is here. And then at 3 pi over 2, we have -1/2 times sine of 3 pi over 2. And sine of 3 pi over 2 is -1 normally. Okay, so this is a 3 pi over 2. This fainter graph is the original one. Normally it goes down to -1 at that point. But because of the -1/2 that's in front of it, we multiply it together. Negative times negative gives us +1/2. Yep, very good. So it ends up being the point 3 pi over 2 comma, and there's a typo here. This should say positive. It should be positive. So if you guys want to cross that off or just change it to a plus, that should be +1/2. Yeah, thank you, Lee. Yep. Yeah, so up here. Okay, and then at 2 pi, we have -1/2 times sine of 2 pi. So we get -1/2 times 0, which is 0. So that's still the same, 2 pi comma 0. So what we see then is, again, the two things that we saw with the example on problem page number, what was it? Page number 9, is that first of all, the amplitude has changed, right? Normally we go all the way up to 1, but in this case, because of the 1/2, we only made it up to a half, so the amplitude is 1/2. That's the first thing. The other thing that changed is the fact that it reflected about the x-axis. Normally it goes up, but in this case we're going down first and then up. Okay, so there is also reflection about the x-axis. Okay. Questions there? Why do we see two lines? We're seeing two lines. This one is just the original sine graph. So this one here is y is equal to sine of x. And we don't need to have it. It's just there as a comparison against the one that we are interested in. So we're interested in the -1/2 times sine of x. So just so that we can see what was affected from the original one, we can compare it more easily if they're both on the same graph. And so there we see that, well, the amplitude has shrunk, right? It went from 1 to 1/2. And it also reflected because now instead of going up first, it's going down. But this one you don't always need to have. This is just for comparison. You guys have any other questions? Okay, so let's try to summarize what's gonna happen. Okay, if we have f of x is equal to a number, let's call it a for any number, okay? If we have any number a times cosine of x, or if we have any number times sine of x, what's going to happen if that number is greater than 1? What change do we see?
Amplitude?
Amplitude, yeah, it's going to change. How is it going to change? Is it going to increase, decrease?
Is it going to increase?
Yeah, very good. It's going to increase. And so amplitude increases if this number is greater than 1. As an example, take a look at what happened on page 5, where we had the 2 times sine of x, and the amplitude went up to 2. Okay. Same thing, page number 6. And for cosine, 2 times cosine, the amplitude went up to 2. So here, I'll just say see pages 5 and 6 for examples. Okay. What happens if that number is 1? It's almost kind of like a trick question. What happens if we have 1 times cosine or 1 times sine?
Stays the same?
It's the same, yeah, it's the same. Nothing really happens to it, right? We just still have cosine and we still have sine. So here, there's no change. Okay, no change from the original. Okay, what about if, I should have said or. What if we have that number being between 0 and 1? So what if it's a fraction or a decimal?
Can you repeat that one more time?
Yeah, no problem. So what if the number is between 0 and 1? Like, let's say, what if we have 1/2 or a third or 0.12, or if we have any number that's a decimal or a fraction, what's going to happen?
The amplitude's going to decrease.
Yeah, very good. The amplitude is going to decrease. And the reason being is because normally sine and cosine make it all the way up to 1, right? But if now that 1 is being multiplied by, let's say, like a third, or by like 0.12, it's going to make it shrink to that value, right? To the whatever the fraction might be, which is going to be less than 1. So the amplitude is going to decrease. And as examples, you can refer back to page, we had one on page, let's see. On page 7 and page 8. Okay, what happens if the number is between 0 and -1? So it's negative, but it's still some type of fraction or decimal. What happens there?
Does it also decrease or?
Yeah, very good. It's still going to decrease, right? Because the fraction, like for example, if it's -1/2, it's going to make the amplitude smaller, so it's going to decrease. What else is going to happen?
A reflection about the x-axis?
Yeah, very good. It's going to reflect about the x-axis because of the negative, right? Good. Okay, so for this one, we can see an example on page 10, the one we just did. What if A is a -1 exactly? Like if I have -1 times cosine or -1 times sine, what does that do?
Is that no change?
Well, it'll be no change to the amplitude, right? So no change to amplitude.
But a reflection about the x-axis.
Exactly, very good. So no change to the amplitude, that's not growing or decreasing, it's still 1, but there will be a reflection because of the negative. All right. And what if it's less than -1?
Decreases.
Well, that's actually the
Oh, no.
tricky part. If we have like, let's say, let's go back to page 9. So here's the example that we had on page 9, where we had a -2 times sine of x. What happens to the amplitude?
It actually increases.
Yeah, it actually increases because the
Yeah.
the yeah, so it's still like, think about it kind of like this. As long as the absolute value is greater than 1, and so the absolute value of -2 is 2, and that is greater than 1. As long as the absolute value of it is greater than 1, it's going to increase. So if you have something that is less than -1, its absolute value will still be greater than 1. So that'll make the amplitude increase. And then because of the negative, we will also see a reflection about the x-axis. So for this one, we can see an example on page 9. Okay. So any questions there with the summary? And now there's this smaller box at the bottom that we're going to fill out. It's talking about the amplitude. And it says, in any case, the amplitude of the function f of x is equal to a sine x, or g of x is equal to a cosine x, is what? Is blank. So what do you guys think? How is the amplitude determined based on this number a that's given? Like, let's think about like some numeric examples, like what we saw on page 5 and 6. Okay, so going to page 5, here we saw that the amplitude was 2 and the coefficient was 2, right? The same thing was true with the cosine. When this number was 2, the amplitude was 2. Or like when we had 1/2 sine of x, we had the number a was 1/2 and the amplitude was 1/2. When it was negative, we have -2, but the amplitude was still 2. So what do you guys think? How can we describe what the amplitude will be based on the number a that's given?
Is that A is equal to the reflection?
So so reflection is kind of I guess determined by the negative.
I'm sorry, I meant the amplitude.
Oh, the amplitude is given by the what, sorry?
A is equal to the amplitude?
Okay, yes, very close. So A,
Is it the absolute value?
very good. It's the absolute value, right? We can't always write the amplitude as A, because in this case, we would be saying that the amplitude is -2. And as we mentioned earlier, we always want the amplitude to be positive because it's a distance. So to prevent that from happening, we always just write absolute value of A. And that will make sure that if this is negative, the amplitude is given as the positive of that number. And if it's positive, then nothing really changes, right? If it's just 2, well, amplitude is 2. Okay, so very good. So just to write it over here on page 11, it's given by absolute value, by absolute value of A. Okay. Any questions there? Okay. So let's talk about period now. We're going to see how a number can change, a number in front of the x can change the period of the function. So we're going to be taking a look at how sine of b times x or cosine of b times x is different from the basic graph. Okay, so let's start by plugging in these values into the function, and then we'll see what's going to happen. The first one is 0, so f of 0 is equal to cosine of 1/2 times 0, which is going to give us cosine of 0. And again, 3 different ways that we learned that we can find what this is. We can look at the unit circle. We can see the basic cosine graph, which is on page 3 of this set of lecture notes. It's this one here. Or you can use your calculator. Since I already have this one here, I'll just use it so that you guys can also see an example of how to apply this. But here is 0. That means that cosine of 0 has to be 1, because that's where we have our first point. Cosine of 0 is 1. And that means that we're plotting the point 0, 1, okay, which is there. All right, next one is pi. Cosine of 1/2 times pi means that we'll have cosine of pi over 2. Because half of pi is pi over 2. So again, if I have this graph handy, I can take a look at pi over 2, and then the y coordinate to that is 0. So we get 0. That means that we have the point pi, 0, which is here. Okay, next one is 2 pi. We have cosine of 1/2 times 2 pi. Half of 2 pi is just pi, so this is cosine of pi. And I have this one handy, so I'll just take a look at what it is. Here's pi. We go down to meet the graph, we make it down to -1. So this is -1. That means that we'll have the point 2 pi, -1, which is down here. Okay, and then for 3 pi, we have 1/2 times 3 pi, which is cosine of 3 pi over 2. And 3 pi over 2 is 0, so we get 0. That means that we have the point 3 pi, 0, which is here. And one more, 4 pi. That is cosine of 1/2 times 4 pi. So that'll be a cosine of 2 pi, which is, again, if you take a look at this, or if you punch it into your calculator, you're going to get a 1. So we get 4 pi, 1. Okay. All right, so remember, these are not straight lines. When we have sine and cosine, we always want to have a curvy graph. We're going to draw a curve passing through those points. And we end up with this. So questions on just finding the points and plotting them, and drawing the graph? And I want to compare it against the original graph. This is just the original f of x is equal to cosine of x without the 1/2 in front of the x. What is the difference? It seems like it's the same, but there's actually something that's very, very different. I'll give you a hint. Look at the tick marks. Yeah, it is longer, Kevin. It takes longer to complete one cycle, right? What was the period of the original cosine graph?
2 pi.
2 pi. Yeah, originally the cosine graph takes 2 pi. How long is it taking here to complete one graph? One cycle.
Of 4 pi, so twice around.
Yeah, it's taking twice as long, right? It's 2 pi. So here the period is 4 pi instead of 2 pi. And this is the original. And this is the one that now has this 1/2 attached to it, attached to the x. So maybe right now we're not quite sure how it's directly related to the period, but I will say this. Okay, so we said it's taking twice as long to complete one cycle, right? We're going all the way to 4 pi. What that means is that in 2 pi radians, in the original length, it's completing how many cycles?
Is
Well,
that
it's not
1/2?
Yeah, very good. It's not even completing one, right? It's completing half of a cycle. So in 2 pi radians, we complete half of the cycle. And notice what number is here in front of the x. Oh, it's this 1/2. So for now, maybe it's a coincidence, maybe it's not, but it is worth noting that half of cycle gets completed when we have cosine of 1/2 x. All right. Now, here's a question for us to reflect on. How are we choosing the x values? Well, the x values, they're being chosen so that they are at 1/4 of the cycle, right? So one full cycle happens in 4 pi radians. And the points that we have are 0 pi, 2 pi, 3 pi, 4 pi. So all of these are 1/4 of the cycle. Okay, so just as something to keep in mind, we are choosing the step size as being the period divided by 4. Okay, so 4 pi divided by 4. And there's a reason why we want to choose it at 1/4 of the cycle. Okay, the reason is that at 1/4 of the cycle, that's when we see the highest point of the graph, when we see the zeros, and the lowest point of the graph, right? If this is the full thing and we divide it into 4 equal parts, we see this. And at each quarter, that's where we reach the, I guess, the important points, the ones that really determine the shape of the graph. Okay. All right, so that's page number 12. Any questions there before we go to page 13?
On the bottom, is that P over AQ?
Sorry, this is P over 4.
Thank you.
Mhm. Okay. All right, so let me just mention one thing before I go to page 13, and that is that we still don't know exactly how to relate the period to this number. Okay, but so far what we've seen at least is that this number is maybe related to how many cycles are completed in 2 pi radians. Okay, in this case, we saw that in 2 pi radians, we only have half of the cycle. So we'll keep that in the back of our heads as we work on this next problem. And so for this next problem, we have sine of 2x, and they already gave us the completed table. So let's just take a look at what points they use. They have 0 for x still. So then we have sine of 2 times 0, which is sine of 0. And then sine of 0 is 0. So we have the point 0, 0. Then at pi over 4, we have sine of 2 times pi over 4, which is sine of pi over 2, which is 1. So at sine of pi over 4, notice that's not, the pi over 4 is not directly labeled on here, so we're going to have to label it ourselves. Pi over 4 is half of pi over 2. So that means that we'll have it here. In fact, since it looks like we're also going to need 3 pi over 4, let's just go ahead and label the rest of the tick marks that we're going to need. This is just like counting. This is 1 pi over 4, 2 pi over 4. Okay, but if we have 2 pi over 4, this reduces down to a pi over 2. And then the next tick mark is going to be 3 pi over 4. Again, because we're just counting. So 1, 2, 3. And then this one would be 4 pi over 4, but it reduces down to a pi. And we don't really need to go beyond pi, so I'll stop there. And then we can go ahead and plot now the pi over 4 comma 1. So pi over 4 comma 1 would be about there. And these we also don't really need because they're labeled here already reduced. So just so that I reduce the amount of clutter that I have on my diagram, I'll erase those labels. Okay, now let's see what happens at pi over 2. We've got sine of 2 times pi over 2, which is sine of pi, and sine of pi is 0. So we get the point pi over 2 comma 0, which is here. Then 3 pi over 4 is, if we plug it in, we're going to get sine of 2 times 3 pi over 4. And the 2 and the 4 are going to cancel and reduce to a 2. So we get sine of 3 pi over 2. And then sine of 3 pi over 2 is a negative 1. So we have the point 3 pi over 4 comma 1, comma negative 1. So that'll be down here. And finally for pi, we have sine of 2 times pi, which is just 2 pi, and then sine of 2 pi is 0. So we get the point pi comma 0, which is here. So we get this graph. And notice there is the original sine graph that has been lightly drawn in there as well as comparison. Okay. And the sine graph usually has a period of 2 pi. What is the period of this graph?
Pi.
Pi. Yeah, very good, pi. The period for this one is pi. And I'll just say versus this guy that has a period of 2 pi for the original. Okay. So remember the observation that we did before. The observation was that when we had the 1/2, it showed us that in 2 pi radians, we had half of the cycle. So if what we're thinking is correct, that would mean that in 2 pi radians, this number would be saying how many cycles are completed.
Two.
2, yeah. And so according to what the observation that we did before, if we were to say, if apply it to this one, we're thinking that in 2 pi radians, we're going to be completing 2 cycles. And well, if in pi radians we complete 1, then yeah, in 2 pi radians we're completing 2. We can extend this further, and it would look like it would look like that, and it would complete 2 cycles. Okay, so notice in 2 pi radians, the graph completes 2 cycles. All right, so it's not a coincidence then. That number is related, does tell us how many cycles are being completed in 2 pi radians. And of course, this is only happening with these 2 examples, but I encourage you to try some other problems, maybe make some up of your own, where you have say sine of 4x if you want. And then what that would say is that we complete 4 cycles in 2 pi radians. Okay, so just to make a note of it, this number is going to determine how many cycles are completed in 2 pi radians. Okay. All right, so let's go ahead and summarize then what we know in this next page, on page 14. If we have a number b, so a coefficient b, and what we're thinking about here is in general having sine of b times x, or f of x is equal to cosine of b times x. And so we have any of those 2 situations, and b is between 0 and 1. Okay. Remember, this is telling you how many cycles are completed in 2 pi radians. So if that number is less than 1, what does that mean about the period?
You'll complete it in less cycles, or?
Oh, well, it's actually kind of tricky because it would seem that way, but let me just write it in words what this is saying. So this is less than 1 cycle is completed in 2 pi radians. So what would that be saying about if it's not going to be complete by the time we reach 2 pi, and originally the period used to be 2 pi, what does that mean about the new period for this function?
It doubles.
It could potentially double, yeah. If b, for example, is 2, then that means that, oh, sorry, actually, if b is, for example, 1/2, then it could mean that we have 2 cycles.
Oh, you guys want to sit in here?
And, yeah, in 2 pi radians.
Oh,
And so,
well.
sorry. So in this case, we have that the period extends beyond 2 pi radians. And I think I might have set that backwards earlier. So let me just be clear. If this number is between 0 and 1, that means we're completing less than 1 cycle in 2 pi radians. Okay. So let's say that this mark here is 2 pi. The graph is not going to finish completing the cycle there. It's going to potentially extend beyond that. So the period is going to have to be something that is greater than 2 pi. Okay, now what is this one saying? Well, this is saying that there will be more than 1 cycle completed in 2 pi radians. Okay, so more than 1 cycle. Is completed in 2 pi radians. Okay, so again, let's think about it. Let's say that this is again our 2 pi radian mark, and I actually have more than one cycle. So that's one full cycle for sine. Let's say we have another full cycle for it. If we're completing more than one cycle, what does that mean about the period?
It's shorter.
It's shorter. Yeah, it's going to be smaller than 2 pi. Okay, so the period shrinks to less than 2 pi radians. Yeah, because now the period is something like, let's say, like pi. Okay, that there would be our period. Okay, so questions here? Okay, and then we'll just fill this up real quick before we call it a day. So in any case, the period of the function f of x is equal to sine bx or g of x is equal to cosine bx for b greater than 0. I'm going to give it to you. Next time we'll talk about why this is the case, but it's always going to be given by 2 pi divided by that number, divided by b. So this one's actually important. It's 2 pi divided by b. And I encourage you to also kind of think about it on your own. Why is this true? Why is it true that the period is given by 2 pi over b? And then notice that we are making a restriction on what b can be. It has to be positive. So what needs to happen if b is negative? For example, what happens if we have cosine of negative 2x? And again, I'll explain a little further why this is true later, but for now, we can, whenever you have cosine of some negative number, like say negative 2x, we always absorb the negative. So we, another way to think of it is you just ignore the negative. These two are going to be equal. Okay, so in the case of cosine, ignore the negative. And I'm going to write something here that we'll talk about later. And that is because cosine has even symmetry. You don't have to worry about it too much, but we'll write it down so it can be there in the back of our minds, and then we'll talk about what that means. If you have sine, then you actually bring out the negative in front. So you write negative times sine of 2x. So what this means is bring the negative to the front of sine. Because sine has odd symmetry. So for the first time, we're going to be taking a look at change in amplitude and change in period together happening at the same time. So as you can see, the table is completely blank. No x values have been given to us. We are tasked with finding what are the important x values that are going to correspond to the highest point of the graph and the lowest point of the graph, as well as the zeros. So we're going to learn how to do that in the next few examples. And in order to get started, I want us to take a first step of finding the period. Now the period, we devised a way to calculate it for every single instance of a sine or cosine function. And that was to take 2 pi and divide it by the number of cycles, which we call b. And b is the coefficient of x always, which is this 4/3. So we have the period is 2 pi over 4/3, which is going to be a 2 pi over 1 times 3 over 4, because we're simply multiplying by the reciprocal of 4/3. Okay, so that's going to give us a 6 pi over 4, which if we divide top and bottom by 2, is going to give us a 3 pi over 2. So we have a period of 3 pi over 2. That's the first step. The next step is to find the step size. And when I say find the step size, I mean find what is the difference between each x value. And if you recall from last week's lecture, in order to find out where the peaks happen or the zeros happen, or the lowest points of the graph happen, they happen at every quarter of the cycle. So what we're going to do is we're going to take the period and divide by 4, because the period defines where one cycle is completed. That means that we're going to take that distance and divide by 4. Okay, so that means taking a 3 pi over 2 divided by 4. Remember, division is multiplication by reciprocal. So we're going to take the 3 pi over 2, multiply by the reciprocal of 4, which is 1/4. And that'll give us a 3 pi over 8. Okay, now to find the x values, that would be our next step. We always start at 0. So x0 is going to be 0. And then the next x values, we simply take the step size and keep adding it to the previous x value. Or sometimes an easier way to think about it is to simply take the 3 pi over 8 and multiply by whatever the subscript of the x value is. So to find x1, we take 1 times 3 pi over 8, which is 3 pi over 8. And that is the same thing as taking 0 and adding the step size. Okay, for the next one, we're going to take 2 times 3 pi over 8, because we're adding 2 of those, right? We're adding 2 of those to 0, or if you want to think about it, is adding 3 pi over 8 to 3 pi over 8, which is just 2 times that amount. And that's going to give us a 6 pi over 8, which when we reduce by 2 top and bottom is going to give us a 3 pi over 4. Right, the next x value will be given by 3 times 3 pi over 8. And that'll be a 9 pi over 8, because this is like a 3 over 1. And finally, x4, that's going to be basically the last quarter, right? This is the first quarter, second quarter, third quarter, last quarter. 4 times 3 pi over 8, that's going to give us a 12 pi over 8, which when you reduce by a 4 will give you a 3 pi over 2. And notice here the last x value is agreeing with the period, and that's usually a good sign. That means that we're on the right track, because we are trying to complete one cycle and finding the quarter of the cycle. So these are all the quarters, and the last quarter should agree with one full cycle, which is given by the period. Right, so now that we have these x values, go ahead and transfer them over to the table the way that I have here, because the next step will be to find the corresponding y values to these x values. So let me just write that down. Step number 4 is to plug the x values into the equation to obtain the corresponding y values. Okay, so for the first one, we're going to have y equals 4 times cosine of 4 over 3 times 0. That is a 4 times cosine of 0. And cosine of 0 is simply 1. So we're going to get a 4 times 1. Okay, so that's just a 4. That means the first point would be a 0, 4. Now, if you take a look at the graph, we're not going to have enough room to plot a 0, 4. So what I'm going to do is I'm going to relabel these tick marks so that they, so that this tick mark instead of being 1 is a 2, and then the 2 would be a 4. Same thing going into the negatives, there will be -2, and this will be -4. That means that 0, 4 is going to be up here. Okay, next x value, we're going to get 4 times cosine of 4/3 times a 3 pi over 8. The 3's are going to cancel, and it's going to give us 4 times cosine of 4 times pi, that's 4 pi, over 8, so 4 pi over 8, but that's going to reduce down to a pi over 2. Now cosine of pi over 2 is 1, so we end up with a 4 times 1, and that means that we have the point 3 pi over 8, comma, this cosine of pi over 2 is 0. So we're going to get a 4 times a 0, which is simply a 0. Okay. Now, as you can tell, we don't have intervals of pi over 8. That means that we are going to have to try and find where those should be marked. Now, what's going to aid us is a little trick that we've been learning in the past couple weeks, and that is that if we take pi over 2 and divide by half, then we're going to get a pi over 4. And then if we take pi over 4 and divide by half, we're going to get a pi over 8. So these are just intervals, or these now are incrementing in pi over 8. This would be 1 pi over 8. This would be a 2 pi over 8. This next one would be a 3 pi over 8, which I'll write here. Next would be 4 pi over 8, but it reduces down to a pi over 2. That means that this would be a 5 pi over 8, followed by a 6 pi over 8, but 6 pi over 8 will reduce down to a 3 pi over 4. Then we'll have 7 pi over 8, 8 pi over 8, 9 pi over 8, 10 pi over 8, but that reduces down to a 5 pi over 4, 11 pi over 8, and finally 12 pi over 8 that reduces down to a 3 pi over 2. And I say finally because if you notice that is the last x value that we're going to be plotting, so I don't need to go beyond the 3 pi over 2. So we'll stop there, and now we'll go ahead and plot. 3 pi over 8 comma 0 would be here. And that means we can go on to the next x value now. That'll be 4 times cosine of 4 over 3 times 3 pi over 4. The 3's are going to cancel, the 4's are going to cancel, and we're going to have a 4 times cosine of pi. Now cosine of pi is -1, so we're going to have 4 times -1, which is going to give us a -4. So the point that we're looking at is then 3 pi over 4 comma -4. Okay, so 3 pi over 4 is here, -4 is down here. That means that that is our point. Alright, y equals 4 times cosine 4 over 3 times 9 pi over 8. This is going to become a 4 times cosine of, the 4 and the 8 are going to reduce down to a 2, and the 3 and the 9 are going to reduce down to a 3. So we'll end up with a 3 pi over 2. Now cosine of 3 pi over 2, that's 0. So 4 times 0 will be, in the end, 0. That means we have 9 pi over 8, comma 0. Okay, here is 9 pi over 8. And 0 means we stay on the x-axis. Last one is 4 times cosine of 4/3 times a 3 pi over 2 that means that we have a 4 times cosine of 3's cancel. 4 divided by 2 is 2, so we get 2 pi. And cosine of 2 pi is 1. So we get a 4 times 1. And that is 3 pi over 2, comma 4. Okay, so here's 3 pi over 2, comma 4. And so finally the last part would simply be to graph according to these points. So use these points as a guide for the shape of the graph. So for cosine, we know that we start up at the top and then pass through 0 and then curve, go down to the lowest point, which in this case is this -4, then curve and come back up, pass through 0, and continue on to the highest point of the graph. Okay. So that's what the shape roughly looks like. If we look at the characteristics relative to the original equation, the 4 in front of the cosine tells us that the amplitude we should have been expecting was an amplitude of 4, right? And because that coefficient of cosine is positive, we do not expect a reflection about the x-axis. And so that's exactly what we're noticing with the graph. We're starting at 4, which is the way it, by the way, how cosine starts its graph. It always starts on some positive y value and then continues to go down. And if you check out the amplitude, well, the distance between the highest and lowest point is 8 units, right? So half of that is going to be only 4 units. So our amplitude here is 4, which agrees with what we're seeing for the coefficient of cosine. Now the 4/3 is dictating what the period is going to be. And this is telling us that in 2 pi radians, we're going to see 4/3 of a cycle. So what that means is we're going to see 1 full cycle plus 1/3 more, because 4/3 is the same thing as 1 1/3, right? So that means that in 2 pi radians, we should see 1 full cycle, and if we continue the graph, we're going to see 1/3 of another one. Okay. Which it's a little difficult to draw, but you can see that there is this complete one cycle, and then this chunk between 3 pi over 2 and 2 pi is going to contain what seems to be 1/3 more. Okay. So that is first example that has change in both amplitude and period. Alright, example number 2 is a bit interesting because we see again a change in the amplitude. We still have a coefficient of 4 cosine, so we can be expecting an amplitude of 4 without any reflection. But now if we take a look at the coefficient of x, which determines the period, we see that negative coefficient. So we want to, again, not deal with negative coefficients of x. That's something that we briefly discussed last week. And in order to get rid of that negative, we're going to use the symmetry of cosine. Because cosine is even, that means that this negative can be absorbed, or in other words, we can just ignore it and say that y is equal to 4 times cosine of 2/3 x, because these two are going to be equivalent. The y values are going to be equivalent for every x value. So we can just simply deal with graphing this instead of the -2/3. Alright, so if we go through that series of steps that we were looking at for the previous example, the first step is to find the period. And the period is 2 pi divided by b, where b again is the number of cycles, or on the equation, it's going to be the coefficient of x. So we're going to get a 2 pi over 2/3, which is the same thing as a 2 pi over 1 times a 3 over 2, multiplying by the reciprocal. And that means that the period is going to be, well, 2's are going to cancel out, a pi times 3, which is going to give us a 3 pi. Okay, the next step is to find our step size. So the step size, as we saw in the first example, is going to be the period divided by 4. So that is going to be a 3 pi, actually I think it fits here, 3 pi over 4. Okay, next step. Well, next step is to find the x values, starting with x0 being 0. Okay, then x1 we can find by taking the step size and multiplying by 1. So 1 times 3 pi over 4, which is just 3 pi over 4. Then x2 is going to be a 2 times 3 pi over 4, which is going to be a 6 pi over 4. And if we reduce by a 2, top and bottom, we're going to get a 3 pi over 2. Next one is going to be 3 times 3 pi over 4, which is a 9 pi over 4. And last one, 4 times a 3 pi over 4. The 4's are going to cancel, giving us a 3 pi. Okay, so we'll transfer over those values. We'll have 0, 3 pi over 4, 3 pi over 2, 9 pi over 4, and 3 pi. These are all the quarters of the cycle. Notice the cycle is completed in 3 pi radians. So if we divide that by 4, we're getting the quarters of the cycle. And now what we have to do is take those values and plug them into the equation. Now just to make our work go by a little bit faster, I'm going to rely on my calculator to do this, because that way I can just simply go ahead and do second ands and change my x value. First thing that I'm going to do is make sure that I switch to radians, and then we can start plugging in. So the first would be 4 times cosine of negative 2/3, and I'll make sure to include some parentheses in here. So negative 2/3 times 0, which is simply 4. Notice that makes sense because negative 2/3 times 0 is 0, cosine of 0 is 1, 4 times 1 is 4. Okay, next value. Notice I'm doing simply second enter so that I can get my previous expression. On your calculator, you can just experiment with where this keyword entry is at so that it can bring up the previous expression. For some calculators, you can just press the up button and that'll automatically bring it down for you. Alright, so we're going to be replacing the 0 now with 3 pi over 4, right? Because we want negative 2/3 times 3 pi over 4. So I'll include some parentheses in here and then have 3 pi over 4. Make sure I'll eliminate that 0, and then I'm going to be missing one closing parenthesis. So that we get 0. Okay, repeat it. But now it's a 3 pi over 2 for the next value. So instead of having 3 pi over 4, we'll have 3 pi over 2. We get negative 4. Okay, then the next one is 9 pi over 4. Okay, so I've got 9 pi over 4. That gives us a 0. And finally, we're just going to have 3 pi. So I'll change this to 3. And we get a 4. And notice these values are not kind of a surprise to us. We chose the x value so that it would give us the highest point, lowest point, and zeros. So the fact that they're coming up nicely this way is a good sign. Alright, so let's see, we're going to need intervals that accommodate for 3 pi over 4, or tick marks that accommodate for 3 pi over 4, 3 pi over 2, and 9 pi over 4. So what I'm going to do is I'm going to take, let's say like 3 pi, draw it somewhere, and divide that interval into 4 equal parts. So this is 1, 2, 3, 4. That'll be my 3 pi. And then half of 3 pi would be 3 pi over 2, so that would be this here. And then half of 3 pi over 2 is going to be 3 pi over 4. And simply what I'm doing there is I'm doing 3 pi over 2 divided by 2, which is 3 pi over 2 times 1/2, which is 3 pi over 4. Okay, that's all the magic that's happening there. Okay, and then if I take a 3 pi over 4, which is the size of this interval, and add it to a 3 pi over 2, I'm going to get a 9 pi over 4. You can verify that on the side again. So if I take a 3 pi over 2 and add a 3 pi over 4, okay, so I'm simply taking the size of this interval and placing it here. So that means taking the 3 pi over 2 and adding this piece, which measures 3 pi over 4. We just want to verify that it really does give us this 9 pi over 4. So this one here, we would need to multiply top and bottom by a 2 in order to have the same denominator. And that would give us a 6 pi over 4 plus a 3 pi over 4. And then adding those two together gives you the 9 pi over 4. And how did I know how to do that? Well, I know that the full cycle happens in 3 pi radians, and when I took that and divided it into 4 equal parts, it gave me 3 pi over 4. So that's essentially the same thing I did, but now on the graph. Take 3 pi and divide it into 4 equal parts, and you'll get these x values. Okay, we're going to be graphing the cycle then. I'll just erase these so they don't get in the way. The highest point is going to be a 4, the lowest point is going to be a -4. So when we draw our tick marks, we want to make sure that we can fit in those values. That means that I'll make this a 2 and this a 4. So at 0 we get a 4, at 3 pi over 4 we get 0, at 3 pi over 2 we get -4, at 9 pi over 4 we get 0, and at 3 pi we get 4. That means that we complete one cycle in this manner. Alright. Now this is supposed to extend all the way down to 15 pi over 4 in the positive direction and to -15 pi over 4 in the negative direction. So we have to figure out where those are. Let's see if we can, kind of figure it out. Well, we said the size of in between the interval is 3 pi over 4. So if I add a 3 pi over 4 here, okay, so if I do this, this is essentially going to become a 12 pi over 4 plus a 3 pi over 4, right? Just rewriting it so I have the same denominator. And that's going to give me a 15 pi over 4. Okay, so that means we only have to extend it to one more tick mark to the right. So that means that we would have, if you punch it into the calculator, there are two things. The first one is we can have an educated guess as to what's going to happen at 15 pi over 4. And well, since these two are equally spaced apart, we can guesstimate that this is going to be, it's going to go down to 0. But we can always verify it by punching it into the calculator. So instead of having this 9 pi over 4, I'm going to replace that with a 15 pi over 4. Okay, now this is giving me a funky answer. This is saying -8 times 10 to the -13. That's because with calculators, they always represent numbers to a nearest decimal place. So this is actually a very, very, very small number, very close to 0. When I say very small number, I mean very close to 0. So it's probably best that we just kind of verify by hand because the calculator is not being too helpful at this point. But if we plug that into this equation, we're going to get y equals 4 times cosine of -2/3 times 15 pi over 4. And that's going to be a 4 times cosine of the 2 and the 4 are going to simplify to a 2. The 3 and the 5 are going to simplify to a 5. So we get -5 pi over 2. And if we look at what is cosine of -5 pi over 2, that's going to be 0. So we're going to get a 4 times a 0, which is simply 0. Okay, so that confirms our suspicions that a 15 pi over 4, we're going to go down to 0. Okay, what do we do beyond that? Because we still need to extend to -15 pi over 4. Well, first things first, let's just go ahead and label the tick marks. Okay, so 1, 2, 3, and 4. This is going to be -3 pi. This is going to be -3 pi over 2. This will be -3 pi over 4. And this will be -9 pi over 4. And I'm quickly getting these values simply by reflecting them over, right? If 3 pi over 4 is -3 pi over 4 is a reflection of 3 pi over 4. Then 3 pi over 2 and -3 pi over 2, well, those have the same distance for 0. Same is true about these last tick marks. All the way down to -15 pi over 4. Okay, then what? Well, then we remember the symmetry of cosine. Cosine, we said, is an even function, and any even function reflects about the y-axis, meaning there are mirror images, the left-hand side and the right-hand side. So if we use this as a mirror, that means that the 3 pi over 4, 0 is going to reflect to -3 pi over 4, 0. The 3 pi over 2, -4 is going to reflect over to -3 pi over 2, -4. Oh, and I think I probably mislabeled this point. This one should have been here. And there. Okay, that's better. Alright, then 9 pi over 4. At 9 pi over 4 we have 0. That means at -9 pi over 4 we'll have 0. And then at 3 pi we have 4. That means at -3 pi we're going to have 4. And -15 pi over 4 will be a reflection of 15 pi over 4. So it'll also have a y value of 0. So we're going to see the graph oscillate in the same manner that it did for the positive x values. Yeah, so that's what we get. Let's check the attributes now. Does it have an amplitude of 4? Well, highest value is 4, lowest value is -4. The distance between these is 8. Half of that is 4. So, yep, it still has that amplitude of 4 with no reflection about the x-axis, right? It started on the positive y-axis, not on the negative. So that looks good. And then the period, we found it to be 3 pi. So period is 3 pi. Does that agree with what we saw here for B? Well, for B, it says, well, you're only going to be completing, if we're looking at the positive version of it, you're only going to be completing 2/3 of the cycle in 2 pi radians. So what that means is that you're going to have to take a little bit longer. You're going to have to take more than 2 pi radians in order to see the full cycle, meaning the period has to extend. And that's exactly what's happening here. We see the period extend beyond 2 pi into 3 pi. Okay, so all is in agreement. For one last example, example 3, we have to graph y equals 2 times sine of negative pi x for x being between -3 and 3. So again, we have that negative coefficient for x. We're going to use the symmetry of sine. Now if you recall, sine is an odd function. And unlike in an even function, we simply can't ignore the negative, or we can't absorb the negative away. For an odd function, what that means is if you have an f of negative x, you bring out the negative in front of the function. So it's negative f of x. Okay, so applying that to what we have here, that means that we're going to end up with y is equal to a -2 times sine of pi x. Okay, I'm bringing out the negative to the front, but there is that 2, so I need to make sure that I bring it all the way outside. So think of it kind of like a negative times a +2 gives us a -2. And now this is the function for which we're going to be finding the period. Okay, so here's step 1. The period is 2 pi over b, where b again is the number of cycles or the coefficient in front of x. So we have a 2 pi over pi. That means that the pi's cancel and we get a 2. The next step is to find the step size. And the step size is going to be the period over 4. That means that we have a 2 over 4 for a final step size of 1/2. Alright, so now we need to find the x values, starting with x0 being 0. Okay, the next x value will be given by 1 times the step size, so 1 times 1/2, which is just 1/2. Next x value will be 2 times 1/2, which is simply 1. Next x value will be 3 times 1/2, or 3/2. Last x value will be 4 times 1/2, which is going to give us a 2. Okay, so we're finding all of the quarters of the period. If the period is 2 and you divide it by 4, you're going to get each quarter happening at multiples of 1/2. Okay. Alright, so now we're going to transfer those over. We're going to have 0, 1/2, 1, 3/2, and 2. And we're going to plug those into our equation to see what corresponding y values we get. Okay, so the first one is 2 times sine of negative pi times 0. So we get 0. Okay, then we have negative pi times 1/2. I'll go ahead and introduce the parentheses here, in which case we no longer need this times. I mean, we can leave it there, it doesn't hurt. Okay, and we're going to get -2. Alright, next one is 1. So I'm just going to delete the 1/2 and get 0. Next one is 3/2. We get 2. Next one is 2. We get 0. Okay, so let's plot these on our graph now. We need to make sure that we have all the way up to 3. So let's see, and that we can draw all of the half intervals. So if we make this, let's see, 1, this would be 2, and then we would have 3 here at the end. Then this would be 1/2, 3/2, and 5/2. And same thing going in the negative direction. We'll have -1, -2, -3. This will be -1/2, -3/2, -5/2. And let's see, lowest point is -2, highest point is 2, so we can make this 1, 2, and then -1, -2. And now we have all of the tick marks that are needed. Let's plot the points. We got 0, 0, 1/2, comma, -2, so that's down here. 1, comma, 0, 3/2, comma, 2, 2, comma, 0. And if we continue the pattern here, well, let's see, at the next quarter, this is already completed one cycle, so we're going to start repeating. We're going to go down to -2 and then back up to 0 to get this shape of the graph on the positive x-axis. Okay, now we continue into the negative x-axis, into the negative x values. If it already completed a cycle between 0 and 2, that means that going into the negatives, we're going to start repeating some values. So this is going to go up to a +2, then down to 0 at -1, down all the way down, down all the way to -2 at -3/2, up to 0 at -2, up to 2 at -5/2, and down to 0 at -3. And here I'm just simply using the pattern of the graph. I know that it's oscillating back and forth between 2 and -2, but you could always verify what the y values truly are by taking the x value and plugging it into the equation. Like for instance, let's say that I wanted to verify that at -1/2 we go up to 2. Well, then we can simply plug it in. Okay, I'm going to replace that 3/2 with a -1/2. And we see that we go up to 2. Okay, so that verifies that. Let's say that I want to verify the -1 now. Well, what I could do is simply delete the divided by 1/2. We get the 0. Okay, so all those y values you can verify by plugging them into your equation. Once you are satisfied with that and convinced, you can start drawing the shape of the graph. Okay, so again, let's take a look at what we were expecting simply by looking at the coefficients of the equation versus what we have on the graph. So once we took into consideration the symmetry of the function and we said, okay, this equation is equivalent to this one here, we now have a coefficient of -2 for sine. So that means two things, right? Last week we learned the negative causes the graph to reflect about the x-axis. So sine normally begins going up and then coming down. This one begins going down and then going up, which is a sign of reflection, which means that it is consistent with that negative being there. The other change we saw from the original sine graph is that we have an amplitude of 2. And well, again, if you look at the difference between the highest point, which is 2, and the lowest point, which is -2, that's a distance of 4. Take half of that and you get 2. So the amplitude is consistent with what we see in the coefficient. All right, what about the period? Well, the period was 2 pi, would originally be 2 pi, but because of the pi, we divided 2 pi by 2 to get a period of 2, and well, that's what we're seeing on the graph as well. And one cycle of sine gets fully completed between 0 and 2, and then if you want to continue the graph, you'll see a repetition of it after the 2, or if you decide to go into the negatives, you'll see a repetition of this portion of the graph happening between 0 and -1/2. Okay, so in any case, we see that the period will indeed be consistent with 2.